This is the CDFAM podcast, with recordings from the CDFAM Computational Design Symposium held in Amsterdam in July 2025. Next up, we have a keynote presentation by Tiffany Cheng, a researcher at Cornell University. She will be presenting on Bioinspired and Biobased 4D printing for adaptive building facades.
All right. Thanks, Dawn, for organizing this event and bringing together this wonderful community. It's my great pleasure to be sharing today the work that I've been doing on Bioinspired and Biobased 4D printing towards my goal of creating an adaptive built environment. So currently I'm a assistant professor at Cornell University's Department of Design Tech. This is actually a recent transition as of 6 months ago. Prior to that, I had spent my past 8 years actually at the University of Stuttgart's Institute for Computational Design and Construction, where I was developing my PhD and then later leading the material programming research group. And throughout my work at Cornell, where I currently direct my new lab called the Multi-Meso Lab, and also throughout my past work in Germany, I want to emphasize that the research that I'm doing is very interdisciplinary. I've collaborated closely with partners from material science to physics to biology and also industry. And this is important because my work at its core is about learning from nature, how to use natural materials more sustainably, but also performatively. So this work requires that we integrate different disciplines. For example, developing new bio-based materials to turn properties that we normally consider as disadvantages, such as shrinking, swelling, warping, into advantages. Also studying biological role models in order to mimic their structural layering and transfer them to emerging technologies like 3D printing. And finally, how to design and program new types of mechanisms whose shape changes and functions are 100% controlled and powered by the environment. So I think by integrating and synthesizing knowledge from these diverse domains, we can then create bio-inspired structures that can change shape without consuming any operating energy. And I present this as an alternative to conventional methods of design and making. So before I go into the details of how all of that works, I want to share a little bit about where I'm coming from. So I consider myself a maker. I've been making things for practically my entire life. I actually built my first 3D printer about 15 years ago, the original MakerBot Cupcake CNC. And besides 3D printing, I've also built a wide variety of projects ranging in size, from origami robots to large-scale art installations, and also buildings when I was working as an architect. And having made so much stuff throughout my life, I became increasingly confronted with the environmental responsibility that comes with the act of making. So I just want to share this infographic, which compares in the year 1900, the Earth's biomass, which you see on the right here, and comparing that to, on the left, the anthropogenic mass, which is the accumulation of all objects made by humans. And when you consider that humans only make up 0.1% of all of the biomass, since 1900, the anthropogenic mass has actually doubled every 20 years. And according to a recent study, the anthropogenic mass has now surpassed the biomass. So, and actually the biomass has even decreased because of because of deforestation and our overall manufacturing activities. So this study really made me realize that the climate problem is really a problem of how we use materials and make things. And a lot of this human-made anthropomass are things like buildings and roads, and manufacturing those construction materials are responsible for 9% of global CO2 emissions. Building operations like heating and cooling, for maintaining comfort in our buildings, that's 28% of global emissions. So essentially over 2/3 of carbon emissions are linked to our overall manufacturing and industrial activities. So in order to address this global problem, I think we need to design our products and buildings to adapt to multiple scenarios to be used and reused into the future. So the question is, how do we make structures that are adaptive? So architects, many of us are architects here. I think there is a long history of speculating on ways to make buildings more adaptive and future-proof. So, for example, the Prada transformer by OMA, it has specialized floor plans on all different sides of this building surface, essentially expanding the usable footprint of one building by rotating the structure with cranes. There's also the Villa Girasole, which was designed to follow the sun's movement throughout the day, but it requires this huge machine to rotate this 1,500-ton mass. And of course, there's the Arab Institute, the Arab World Institute, which is a famous example of a kinetic facade with over 16,000 apertures that control the amount of light entering the building. But like the previous examples, it's very costly and complex to maintain. The facade itself is no longer adapting autonomously. And in the case of the Villa Girasole, it's actually at the risk of demolition. So you don't see a lot of these structures operating over a long term. However, in biology, organisms also move and adapt, but in a very different way. So plants respond to their environment by changing their shapes and properties through growth and other mechanisms. I'm really interested in the mechanisms of seed dispersal that you see on the bottom row here, from the folding of pollen grains to the exploding cucumbers on the right. And these are really interesting because they don't require any active metabolism to function. So let me explain that with my favorite example, the pine cone. It really nicely illustrates the example of how the material structure and function are so tightly integrated that it can reliably open its scales without consuming any metabolic energy. And interestingly, it's actually dead. It's a dead tissue when it falls from the tree. And indeed, my partners from biology have actually found a 14 million year fossilized cone that can still open and close. So this incredible robustness that we observe in nature often is due to the material structure. And you can see in this on the right here, the cellulose microfibrils, which are arranged in these two directional layers. And this bilayer structure is what causes the pine cone to swell or shrink in response to moisture changes. So my personal goal has been to investigate how we can apply strategies such as these from biology to the design and manufacture of our products and buildings. For example, maybe one day we'll have building skins that autonomously provide shading or ventilation depending on the weather. So my personal dream is to get rid of active heating and air conditioning. So in the next projects that I show today, I'm going to be introducing my previous doctoral research in working towards this goal. So I'm going to explain fused filament fabrication is really actually conducive to emulating the fibrous structure of biological materials. And this is a process called 4D printing. So even though the printers and materials are very cheap and accessible, one of the core challenges is how do you even design these structures? How do you even 4D print something that can change shape? So how it works is that through the process of extrusion, you leave these anisotropic features on the material layer. And when you print that with a hygroscopic material like wood, it swells or shrinks directionally. When you print a less swellable layer on top of this existing layer, similar to the pine cone structure that we saw earlier, the resulting bilayer bends in one direction when swelling and the other direction when shrinking. So by programming the extrusion path with a 3D printer with different parameters, such as spacing, layer height between the paths. You can control bending in different directions. You can control the amount of bending, and you can also control the speed of bending. And by combining and stacking together these different bilayer building blocks, as I call them, you can expand the geometric possibilities. So this extrusion process is kind of like an analog material code that tells the material what shape it should transform into. Through a lot of experimentation, I developed a computational fabrication workflow for configuring these assemblies of bilayers within the established CAD platform of Rhino and Grasshopper. And this allows us to preview the shape change of the combined bilayers and finally generate the low-level machine code that can create an intricate mesostructure, as you see on the left here. So no STL involved, directly machine code. And this allows designers to focus in on the high-level design without needing to worry about how to organize each of the individual toolpaths or needing to learn how to write the machine code. And that allows us to automate the production from a digital design to physical objects. And we can create many types of material transformations that you can see here, such as bending, expanding, folding, stretching, and even double curvature. Okay, so the next challenge deals with how do we transfer and upscale these methods I just showed that are on the desktop 3D printer scale, the hobbyist 3D printer scale, to a industrial robotic platform. And in terms of the materials, we're using construction materials here. Wood is a really well-known and easily scalable material, which can also be used for self-forming bilayers with high actuation forces, albeit it has a very low resolution of programmability. On the other hand, 3D printing enables a high resolution of detail in customizing material properties. So in order to combine both of these materials into a hybrid system, we developed a large-scale additive manufacturing platform with multiple integrated end effectors, which includes a vacuum gripper here for the pick and placement of the wood bilayer actuators, and also a large format extruder for the 3D printing of metamaterial structures. And that allows us to produce this hybrid structure in which the wood and the 3D printed pattern are working together to cell shape up to the meter scale. So in transitioning from the desktop scale to the large scale robotic extrusion, it's necessary to make some adjustments to things like the extrusion toolpath, which had to be continuous and non-crossing due to the larger nozzle and the pressure built up inside of the barrel. The 3D printing parameters also had to be recalibrated, although the general relationships between depth, thickness, ratio, geometry remained the same. So using the geometry, we can actually modulate and physically program areas with graded stretching, areas of high anisotropic stiffness, and also program bending in different directions. And so this biocomposite structure, just by acclimating to the moisture content in the environment, can transform from that flat state to a doubly curved geometry without any mechanical force, without any subtractive manufacturing, without any operating energy. And so based on this large-scale additive manufacturing platform that we developed, my master thesis students also explored the unique properties of auxitic metamaterials, which when bent, form surfaces with variations in double curvature. So they exploited this property in self-forming bending active shell structures in which the wood is distributed and embedded within a surface with this honeycomb and inverse honeycomb pattern. And and depending on the pattern, this results in positive and negative Gaussian curvatures. And in other words, that's like a dome-like curvature or a saddle-like curvature. So by modulating these patterns across a functionally graded surface, we were able to fabricate this 3-meter-long structure with varying Gaussian curvatures across the surface. And it took 13 hours to print even with all the hiccups, as this is our first time printing something this large, which is really fast considering the size and curvature of this structure. So I want to give a quick shout out to Laura, Karen, Etta, who were the thesis students who worked on this project. So in the next project, I want to share how we can translate the working principles from biology to design and engineering applications. And this is a project that was done in collaboration with the plant biomechanics group, but also the university hospital at Freiburg University. And I use orthotic devices as a motivating example because there's a need for both customization and adaptation in specific patient pathologies. Proper fit is extremely important, and 3D printing has indeed become a very popular technique for customizing personalized splints for a variety of shapes and sizes. However, it doesn't address the muscular atrophy that typically results from immobilization. So this is when your limb basically gets thinner if you're wearing a cast. And the reason why, if you've ever broken your bone, you had to go back to the doctor every few months to get your cast refitted. So together with my biologist partners, we found this very interesting plant, the air potato plant, which has a very clever strategy of climbing smooth supports without slipping off. And it generates high squeezing forces onto the host structure through these stipules, which are located at the base of its leaves. And when they grow, they expand, thereby tensioning the system. So we studied and abstracted this tensioning mechanism to 4D printing. The squeezing behavior basically happens in two phases. First, the stem helix loosely winds about an existing structure, and then it pushes outwards with the stipules in order to stiffen the stem helix. And then we abstracted this and transferred them into a twisting bilayer strip called the helix mechanism, and the second part is this bilayer flap that we call the pocket mechanism, and that creates a pocket of space between itself and the helix on top of which it sits. So here's an overview of the biomimetic process, where we took that tensioning strategy from the air potato plant and transferred it to 4D printing through the design of the helix and pocket mechanisms. These two mechanisms can be individually tuned and combined into a single material system. And then we could evaluate it for applications where the fit and grip are important. So we tested the 4D printed material system that we created and evaluated the ability for it to stay gripping onto a support pole. So we here you can see the pure helix mechanism gripping onto a 30 millimeter diameter pole and self-releasing after 40 minutes. I'm not sure why the videos are not working, but in comparison, the helical system without the pocket mechanisms can actually stay gripping onto even smaller diameters and stay gripping for over 3 hours during moisture uptake. Okay. We also measured the squeezing forces of the 4D printed material system and compared the different combinations of the two mechanisms. So here you can see on the bottom, the helix mechanism by itself without anything else generated pretty low forces. And the addition of these pocket mechanisms in low and high densities generated increased forces to varying degrees. But the most effective strategy for generating squeezing force was to delay the actuation of the pocket mechanisms. Now, the doctors who would actually use this self-tightening mechanism are likely not experts in digital modeling. So we created this design workflow in which physicians could physically prototype designs directly onto the patient's body, 3D scan and digitally analyze the curvatures, and then generate the fabrication data for 4D printing. And this is important for adoption outside of the lab. So this is the design of the splint with the Bioinspired mechanism, which self-tightens around the wrist and forearm at varying curvatures. But what's the most interesting takeaway for me is that we were able to generate similar ranges of forces as the air potato plant while mimicking the stipules in low quantities, which is how they are found in nature. But if we increase the number of these stipules and delay their actuation, we can actually measure higher forces. And so it was exciting to see that computational design and 4D printing allows us to extend beyond what nature can achieve. Okay, in this last project, I'm going to talk about whether or not we can apply bio-inspired 4D printing to the real world in actual buildings, which is something that I kind of talked about in the very beginning. So this is a collaboration with the Cluster of Excellence in University of Freiburg, the LiveMats, and also the Plastics Technology Institute at the University of Stuttgart. And the goal was to adapt the foundational scientific research that we developed over the previous projects that I introduced to a real building demonstrator application. So there are new challenges in integrating the self-shaping design with real environmental and weather conditions, and this happens across a longer time scale than we were used to. But also, if we can even scale up the 4D printing manufacturing process at the level of a building facade. So using this research building project that we had at the ICD, which is called the LiveMats Biomimetic Shell building, we use this as a case study to design the self-shaping adaptive facade according to its very specific building conditions. And we worked with the global design team of the building project to position the building on site so that the south-facing orientation of the building allows us to gather the maximum amount of solar heat possible. And that means that during the winter months, we needed to design the 4D printed shading elements to open to allow solar heat to enter the building. But in the summer months, then they should close to block out the high heat loads from entering the building. So how do we program shading for the different seasons using a humidity reactive material? So in temperate climates, such as in Germany, but most likely here in the Netherlands as well, there's a reliable link between temperature and humidity. So if you take a look at a typical winter day, you can see that the humidity in blue remains quite high, while the temperature in red maintains a very low trend. And on a typical summer day on the right, you can see that there's much more daily fluctuations in temperature, but the humidity always remains, it always maintains this inverse relationship. And so when we designed our shading elements so that means we had to design our shading elements to curl and open when humid and then flatten and shade when dry. And we also needed to match the response time of the material to the time scale of weather changes in Freiburg, where the building would be. And so together with material scientists, we co-developed a highly responsive 3D printable filament material, which was consisting of cellulose locally sourced from a company in Germany. We went through then a very intensive testing process in the lab using an active climate micro generator to cycle many times, alternating high and low humidities. There we discovered that our LED adhesives are not really robust against high humidities. But we were happy to see that our 4D printed elements could continue to operate against these disturbances and faced by multiple attacks. Now, in order to test the performance under real weather conditions, I built a facade mock-up in Stuttgart, which mimics the same orientation and height as the target building in Freiburg. There's very similar weather patterns. And there, the 4D printed elements were then exposed to the full range of humidity, temperature, and UV effects over all of the seasons for over a year. And then with the assurance from our extensive testing, we then rented a total of 4 3D printers to fabricate almost 450 bespoke shading elements. So each of them were unique. And because of this very material efficient structure, Each of these only took, on average, 20 minutes to produce. And the whole process of 4D printing the facade took 17 days and less than 6 kilograms of material. So all of these 4D printed elements were then pre-assembled at our lab in Stuttgart onto thin aluminum strips through this integrated press-fit 3D printed connection. And each of the windows then went through a short testing phase just to make sure there's no defects before we actually put it into the building. So in the end, we had these pre-assembled windows, very extremely lightweight, that we could then pack it into one minivan. We could drive it onto the construction site and then unload and install it onto the roof without any cranes or heavy equipment. I also want to mention that we designed this facade system with operable glass doors, which means that we can always access the window cavity if we need to repair, if we need to even remove the facade system if needed. And also that the windows are vented on the top and the bottom, which allows those materials to acclimate to the temperature outside. And so there it is, the real thing. And this is, to my knowledge, the first 4D printed weather responsive facade. I'm proud to say that it's also a public building, which is open to students, faculty, visitors at the University of Freiburg. And here's a view from the inside. So this is just a couple days after the installation. I was very happy to see that the facade was working immediately. And you can see on the morning where it's relatively cool, they're open. And then as the afternoon heats up, they're closed. And I also want to share an anecdote, which is that there are sensors on the top and the bottom of each of these windows where I'm still monitoring the results. And the electronics actually took over a year to get working. It took over a year to get AC power onto the windows, whereas the material just started working immediately after installation. And so this is just a kind of video of that same day, a time lapse that I took. And again, it requires zero operating energy, demonstrating resilience against things like power outages, or the complex engineering and constant maintenance that's required for comparable electromechanical systems that I showed in the very beginning of my presentation. And what's exciting to me is that this solution has the potential to be economically scalable because we were able to scale up the 4D printing process to the level of building facade using very commonly available, very affordable 3D printing equipment and the most abundant biopolymer on Earth, which is cellulose. And now I want to move a little bit into my future and ongoing work at Cornell University. So one of the limitations of such a weather-responsive system is that many people who are in buildings want to be able to control their surroundings. We're so used to things like the shades that we can just open and close. So overriding this passive functionality is definitely a challenge. And currently I'm looking into modeling the dynamics of self-shaping materials and their interactions with human behavior, with the weather cycle and occupant comfort over multiple time scales. And still, I have this dream of completely getting rid of aluminum in my facade or the steel in the structure of buildings. So I'm currently also looking beyond facades using a monomaterial system enabled by advanced robotic manufacturing methods and multi-scale additive fabrication. So imagine that we have this industrial robot here with nano to microscale fabrication all integrated in one workflow. Now, aside from the building scale, I'm also really interested in body scale applications. We saw a lot of work from the apparel industry, the footwear industry, and I think adaptation for the body requires a much faster response time than in buildings. And so using the human body as a stimulus, for example, human sweat, poses some really interesting questions about adaptability. And working on the scale of wearables will force us to improve these axes of performance. The scale and application is also much closer to transfer to the market. So I think that having some projects with a direct industry partner is really important for keeping the needs of the real world and the transfer to actual products in focus. And I've talked a lot about material programming, but for a truly adaptive and future-proof environment, we need to talk about material reprogramming. So what if we could unlock functionality at vastly different timescales to respond to different stimuli conditions? And so imagine we have a building facade that grows like a climbing ivy, passively regulates comfort in the building, learns and adapts to climate change, and finally self-decays at the end of its life. So to this goal, I'm really interested in studying amplification mechanisms like curved crease origami structures and bistable geometries in order to create materials with advanced computation and logic. So I'm gonna restart this because I really like this video and I hope it shows this time. Okay. So there's still many lessons to learn from nature on how materials, natural materials can be performative yet sustainable. And that's the mission that I'm continuing at the Multi-Meso Lab at Cornell, to pinpoint how we can harness the inherent characteristics of natural materials to perform even more advanced functions and showcase that bioinspired design and making is a credible pathway to overcoming the competing resources between nature and technology towards a future where our technologies are no different from nature. So I'm really excited to hear your thoughts and possibly ideas about this work. Thanks a lot for your attention.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.